Güzel. Sen sonra okay, so then you will also send the slides to us so that we can post it in our institute website.
Sure, sure. After the talk, I can also, I mean, I can also remove the pause comments.
Okay. Yeah. Or otherwise, you will send 200 pages. Okay. So now I will introduce you. Welcome to the Higher Structures seminar series. So we gave a pause because of the terrible earthquake that affected all of us in the southeast region of Turkey and Syria. So we are really sorry for that. Now our speaker is from University of Edinburgh, Yusuf Barıs Kartal, a young research mathematician, and he will talk on Frobenius maps in symplectic topology, which is a joint work with Doran Kote. Yeah, thank you.
Thank you very much for the invitation. It's a pleasure to speak here. And I hope everyone's families, relatives, friends are doing fine related to the terrible disaster that we had a couple of weeks ago. So I'm gonna talk about some constructions and some structures on some known constructions in symplectic topology. So first, the Frobenius maps that we all know from the first algebra class are the power maps, right? If you have a prime P, then the Frobenius map is the map that sends X to its Pth power. And this has topological incarnations too. So it's a well-defined ring homomorphism over characteristic P, and it extends characteristic P, and it has geometric importance. For instance, the fixed points of the Frobenius is the FP points, the rational points of where it is over FP, and there are analogs of the trace formulas in differential topology in arithmetic geometry too. So you can count FP points on varieties using the action of Frobenius, for instance, on various cohomology theories. And so as the title suggests, this has topological incarnation. So for like the simplest one is if you have a topological space N, and if you consider the free loop space, the space of maps from S1 to N, okay? So you can then define the Frobenius map on the free loop space as the p-fold covering map. So basically you take a loop and you trace it p times faster and p times. In circle coordinates, it can be written like this. It's you replace gamma of z with gamma of z to the p. And in real coordinates, you can also describe it like this. You replace gamma of t with gamma pt. And geometrically, well, as I mentioned, it's the p-fold covering of a given loop. Okay. And so the free loop space is more structured than this. So there's actually a circle action. It's the loop rotation, right? You rotate every loop, and the fixed points of the cyclic group lying inside S1, fixed points, the points fixed by the rotation by 2 pi over p coincide with the image of the Frobenius. So these are the loops that are p-fold covered. Okay. And Frobenius was actually an identification of the free loop space with the CP fixed points. And the Frobenius map, meaning like the p-fold covering map, is compatible with the circle action, except in the target you have to consider the action that's p times faster, or the other way. Yeah. Sorry, the other way. Yeah. What I mean is, like, the action on the CP fixed points is induced by by the identification of S1 with S1 over CP. So a space satisfying such things, satisfying such properties, is called the cyclotomic spectrum. Any questions so far?
Yes, can you explain again what is this Frobenius is an identification of Ln with CP
Yeah.
fixed points item?
So, so the Frobenius, what I call Frobenius on the loop space is just the map that sends a loop to its p-fold covering, right? You have a loop, you trace it, trace the same path, but p times faster and p times.
Is this map injective?
Yes, that's injective. Right? Because if you look at the image, then the segment between 0 and 2 pi over p determines the original loop.
Okay, okay, I think I understand now.
Yeah. So thanks for the question. So this is an injective map, and its image is exactly the set of loops where that are fixed by the rotation by the pth roots of unity. Any other questions? I see something in the chat. Yeah, I'm gonna come to that. I mean, Ln is when I mean by this, I mean like the suspension spectrum of Ln at a base. You add a base point and you take base suspension spectrum. That's what I mean by Ln is an example of a cyclotomic spectrum. I'm not a sigma infinity. I don't know how much alienating the word spectrum is, so I will make a brief introduction to that, but okay. So I'm going to define cyclotomic spectra. First, it's just a crash course on spectra. So for today's purposes, if you have never seen the notion of spectrum, you should think of it as a generalized space. Whenever you hear, if you have never heard of this word in the context of topology, stable homotopy theory, you should think of a space, a topological space, whenever you hear the word spectrum. So the examples is every space gives one. Like every space gives rise to one spectrum, and spectra represent generalized cohomology theories. So in particular, for instance, the cohomology with coefficients in any abelian group is an example of a spectrum as well. So this is called Eilenberg-MacLane spectra. And you also have other spectra like real K-theory spectrum, complex K-theory spectrum. For every generalized cohomology theory or homology theory, you have a spectrum. And a cyclotomic spectrum X is a spectrum carrying an action of S1, carrying an action of S1 and an S1 equivariant identification of X with the fixed points of the induced action, the restricted action on CP. So here the second part is the geometric fixed points of the pth roots of unity lying inside S1.
Sorry, so when you say every space gives one, you mean not, but every space gives more than one, right? You mean?
I mean, what I mean is, if you have a space, you can take its suspension spectrum.
Yes, but you can take others too, right? There are others. Is there no other construction of a?
Sure, you can take also shifted suspension spectrum.
Okay. And when you say Eilenberg-MacLane spectra, for example, that's
so that's
that
the
doesn't have
sequence.
an input as a space.
No, the sequence of spaces. These are the Eilenberg-MacLane spaces, KANs.
Okay, I understand. Okay, so that's a special.
Yeah, it's not actually a suspension spectrum. It doesn't come from a space.
Yes. Okay. And what is the geometric fixed points of spectrum?
Yeah, so I won't really discuss this. So for that, you need to have a genuine S1 action. You can think of this like if you think of X as a space, then the geometric fixed points are the actual space level fixed points. The more precise statement is if X is a suspension spectrum of an f of a space with a genuine S1 action, then the geometric fixed points of the suspension spectrum coincide with the suspension spectrum of the fixed points of the space.
The action doesn't have to be free. Even it's
No.
not free, it's okay. Okay. You don't have to resolve something.
Not as far as I know. No. There are bunch of notions of fixed points. This is the geometric fixed points. Other questions?
Can I ask one question? So, if we have a dictionary between this theory and number theory, for example, this cyclotomic spectrum corresponds to what kind of object, like cyclotomic fields, or I am sure the primary motivation of the cyclotomic spectrum comes from number theory, because you started. You started with talking about the Frobenius map in characteristic P rings and so on.
So, I don't exactly know an analogy, like a dictionary between them. What I can say is there's a construction called topological Hochschild homology, and when
Yes.
you apply this to say algebras or algebras over characteristic P, or more generally, like to dB coh of varieties over characteristic P, you obtain some well-known cohomology theories like crystalline cohomology, not as topological Hochschild homology, but as topological periodic cohomology. Or
This is Scholz's work, right? Scholze.
Yeah.
Okay. Thank you.
Because before Scholze, not before Scholze, but
This is not Scholze, right? This is earlier than Scholze.
this is genuine ones are earlier.
Thank you.
Any other questions? Okay. So I already gave the example of free loop spaces, and I already mentioned the topological Hochschild homology is one of the primary examples. So our goal is to construct cyclotomic spectrum on non-invariance of symplectic manifolds. Previously, I was starting with a long motivation. This time I pushed it to the very end, and it's a lot more brief. So, but okay. I think, yeah. So some notes is that this can be used to recover cohomology theories. I just mentioned this. Associate to varieties of FP, the topological Hochschild homology, with this circle action. This can be used, for instance, to recover things like crystalline cohomology from the derived categories of varieties over FP. So there's some recent interest by number theorists like Nicholas Scholze, Batmorov, Scholze. A lot of stuff is appearing nowadays. And there's I think I mentioned this, there's a modern way of defining the cyclotomic spectra, we discussed this using the homotopy fixed points and the Tate construction. So I'm not gonna say in construction, and I will say brief things about homotopy fixed points. So you should see Nicholas Scholze. And
so you won't say, but which Tate construction in which subject is this?
Tate construction in topology. If you have like in a stable covariant homotopy theory, you can find a definition if in Nicholas Scholze in the topological.
But it's not like Tate construction of uniformization, for example. It has nothing to do with that.
You mean Tate constructions and stuff like Eloquin, Zhao, and or Chilbeck, whatever, like this Tate construction where you have this extra.
Like Tate curve. Maybe I'm thinking about Tate curve. Maybe that's not called Tate construction. Okay, so I just don't know what this Tate construction is. Okay.
Okay, I'm not gonna say anything about Tate construction, so it's not gonna. Thanks. And we will also produce S1 equivariant maps to homotopy fixed points with respect to the, homotopy fixed points of the CP action. So this is actually stronger than a cyclotomic structure, and it's easier to explain. Okay, it's called Frobenius lift in Nicholas Schulze, but okay, so I'm gonna give a crash course in symplectic topology, in symplectic geometry. So a symplectic manifold is a manifold endowed with a closed two form omega, such that the omega to the n, the top power of omega, is a volume form. And and we will always deal with exact symplectic manifolds. So it locally models the phase spaces in classical mechanics. So the first example that anyone ever sees is the 2n-dimensional Euclidean space with this two form, dpi, dqi. Here qi coordinates represent the position and pi coordinates represent the momentum of a particle in the n-dimensional space. Generalizes a little bit. Every cotangent bundle is an example of a symplectic manifold. And if you have a function, usually called Hamiltonian, on M, it leads to a well-defined vector field denoted by xh. It's given by the rule that I wrote here, dh. So conventions sometimes change, but it's dh equals omega, and you plug xh, the vector fields. I mean, omega gives an identification of the tangent bundle and the cotangent bundle, and under this identification, the differential of h corresponds to this so-called Hamiltonian vector fields. The Hamiltonian vector field. It's the definition. And the example is when you take your Hamiltonian to be the kinetic energy plus the potential energy, the total energy. Then this is of a particle of unit mass. This by Newton's laws. So in particular, the existence of closed trajectories of the Hamiltonian vector field is important in dynamics, and lots of tools have been developed for this. So to address related questions, Floer homology was developed. And so homology theory for symplectic manifolds, I will say more about this, is an analog, infinite dimensional analog of Morse homology. Okay, and so Floer homotopy theory is not as new, but has found more recent interest, and it can be used, for instance, to sharpen the lower bounds on the number of Hamiltonian orbits. I said more will come, but more will come only about Floer homology and Floer homotopy, not the numbers of Hamiltonian orbits. And these things like Floer homology relate to cohomology theories in algebraic and arithmetic geometry via something called mirror symmetry. I won't say anything more about this, or maybe a little more at the very end. Questions? Okay. So let's see. So first I will discuss the Morse homology, and Floer homology will be a lot easier once we see Morse homology. So if you have a closed manifold and if you have a Morse function on n, you can consider the critical points of f. So for a fixed generic metric on n, you can take the gradient vector field of the Morse function. Okay, so the zeros of the gradient vector field are the critical points of f. And you consider the trajectories of the negative gradient vector field from one critical point to another. So for generic metric, those form manifolds. I denoted them by MPQ. And you can these manifolds can be compactified. It's a bad sentence. They can be compactified to manifolds with corners by adding broken trajectories. There will be some pictures. Here's a picture. Okay, so here's a surface homeomorphic to the sphere, and it looks like this. The function f is the height function. It has 4 critical points. I draw them in blue: P1, P2, P3, P4. So from P1 to P3, there is only one trajectory, and same with P2 to P3, and from P3 to P4 there are two more trajectories. Okay, so those are like trajectories of the gradient vector field. And from P1 to P4 and P2 to P4, the space of trajectories is one-dimensional. I mean, trajectories up to translation, of course. So I wrote this here. So it doesn't matter we compactify the zero-dimensional ones. These guys are just points. And from P3 to P4, you get 2 points. And from P1 to P4, you get spaces of trajectories as homomorphic to R. And you can compactify this by adding the trajectories, the two broken trajectories. A broken trajectory is a trajectory from P1 to P3 and a P3 to P4. So you add this broken trajectory and you compactify MP1, P4, for instance. So you add two of them because you have two broken trajectories from here to here. Okay. Any questions on this picture? Okay. So I continue Morse homology. So this was just Morse theory so far, not homology. But for simplicity, I take the coefficient field to be F2 here. So the Morse chain complex is defined to be the span of the critical points of F. In the example in the previous page, it was just it's spanned by 4 critical points, P1, P2, P3, P4, and it's graded by the Morse index. And you define a differential. Okay, to define the differential, you just count the trajectories from between the points of index difference one. So you look at the points where the dimension of this moduli space of trajectories up to translation, of course, is 0. And those moduli spaces give you the matrix coefficients of the differential. Okay. So I mean, is like, you take a critical point, you take dp. dp is given by this formula. The coefficient of q is the number of elements in zero-dimensional moduli spaces of trajectories. And to show d square equals 0, you use the boundary structure. Namely, the boundary, like when you have one-dimensional moduli space trajectories, the boundary has 0 elements modulo 2. And you can actually replace F2 by Z by orienting the moduli spaces. And instead of, just putting numbers here, you will use the sign count. And the homology of the Morse complex is actually independent of F and G, and it computes the cohomology. Okay. So, okay, everything's clear with this? Have I lost anyone? Okay. If you are unhappy about anything, just let me know. Okay. So this, but the construction. Sorry, coming from me, right? Let me just close my. No, it's not coming from me. Okay. Okay, so this construction loses the data of higher dimensional moduli spaces. To define the matrix coefficients, we just use the zero-dimensional moduli spaces, and to show d square equals 0, we just use the boundary structure of the one-dimensional moduli spaces. But the trajectories can break more than once, and there are higher dimensional moduli space of trajectories. So here's the picture. So the blue ones here represent the critical points, and as you send gradient trajectories to the limits in the red, it breaks this point first, then it breaks twice, and on the right it can break thrice. So those are all perfectly valid broken trajectories, but the previous construction loses this data completely. So let me say a little more about this. So how do you say anything about the homotopy type using the Morse theory? So I took this title Morse homotopy, but it actually has a different meaning in the literature, so it's not the actual name. So it's an idea of Cohen-Jones-Siegel that you can organize all the trajectories, moduli spaces, in a structure called the flow category. So the objects of the flow categories are, in the previous example, are just Morse critical points, and the morphisms are broken gradient trajectories. And you can define geometric realization of this. I'm not going to attempt to do that right now. When you have two critical points, you apply one-point collapse to the moduli of trajectories between them, and then use that to define the geometric realization. And this recovers the stable homotopy type of the manifold that you have started with. So you can now evaluate n against every extraordinary cohomology theory, any generalized cohomology theory using Morse theory.
So can I ask a general question?
Sure.
So, it's like when you just define Morse homology, as you say, you just use this data of zero-dimensional moduli spaces and throw out all the other higher dimensional moduli spaces.
Mhm.
But when you put back the data of this higher dimensional moduli spaces, it seems like you're going to get like a lot more, some kind of completely different kind of structure, but you just kind of go from homology to homotopy type. Why is that? Why are there kind of, it seems like kind of this dimension zero part determines kind of a big part of the whole thing for some reason.
Mm-hmm.
Do you know why? Is there a...
So it only determines the determines the homology, right? It's the
Yeah,
extraordinary.
but I mean, going from homology to stable homotopy type, yes, I understand it's finer information, but it's not like earth-shattering kind of going, because there is a lot more data kind of a priori, right?
Yeah.
Yeah, maybe there may like in Floer homology, is it the same? Kind of, it's the same, right? It's
Sure. I mean, you get other stuff like the
but you don't get like really, you get like, instead of homology theories, you get cohomology theories, you get like generalized homology.
Well, I mean, that means pretty much everything, right? From cobordism to K theory and topological K theory and stable homotopy type, right? The stable homotopy groups are there.
Yeah.
So stable homotopy, like it's like almost entirely determining the homotopy type, a stable homotopy. It's stable homotopy type. So I think one related question is why for homology, for instance, just zero and one dimensional is enough?
Yeah, maybe that's a better way to phrase the question. I don't know. It seems like there is a big gap, but you actually recover a lot by just looking at the zero and one dimensional part.
Mm-hmm.
And you don't even really look at the one dimensional part, right? That's just used to kind of show something.
Yeah.
Yeah, I mean, I thought maybe there was some answer, but it's not a very good question.
No, it's good. I'm not sure. I think the related question is why for homology you only need 0 and 1. I mean, of course, out of a floor category you can define floor homology completely, but for instance, why passing to homology is like smashing with Eilenberg-MacLane spectra and taking the homotopy groups, stable homotopy groups. I don't really know why exactly the taking smash product with Eilenberg-MacLane spectra loses the higher dimensional information. My guess would be that this is something related. It somehow relates to the fact that like the boundaries represent 0. Boundary, like if you have, for instance, a manifold with boundary inside something else, the boundary, the homology class of the boundary is 0 in this case. But that's just a guess. That's a very fancy philosophical guess. So I don't really know the answer.
Thank you.
Sure. Okay, so floor homology is slight generalization, well, not slight. It's a generalization. So if you have a nice symplectic manifold, take a function, a Hamiltonian function as before. So this time I sinisterly added an S1 here. That means it's time dependent. Okay, meaning like, Hamiltonian was representing the total energy, but energy is no longer conserved, for instance. And you fix a generic complex structure on M. Okay, there is a little lie here, but I'm not going to say it right now. And you can define the action functional. So it's Morse, as long as your complex structure is generic enough. So, and the critical points are given by the one periodic Hamiltonian orbits, the one periodic trajectories of the Hamiltonian vector field associated to H. So the gradient trajectories are given by holomorphic maps from the cylinder to M, holomorphic with respect to the chosen complex structure. You can think of M as a Kähler manifold, like something with a symplectic structure and with a complex structure. And the gradient trajectories of the action functional are given by holomorphic maps that are asymptotic to holomorphic orbits, Hamiltonian orbits at plus and minus infinity. Complex is denoted by CFHJ, is called the floor homology. Well, its homology is called the floor homology. And well, under some assumptions, it's independent of H and J. And so the picture here. So the blue circles here represents the orbits, the one periodic orbits of XH, and the red cylinders are the holomorphic cylinders. So defined by this boost matrix of the different, like if you think of differential as an operator, the matrix coefficients are given by cylinders. And when H is quadratic at infinity, when it behaves in a certain exact symplectic manifold, then you denote the floor homology by SHMZ, and it's called the symplectic cohomology. That's an invariant of manifold. So a small note here, it doesn't really compute the homology of the loop space. I mean, we talked about Morse homology. And with the homology of LM. But if you have a cotangent bundle, then this thing is given, of course, up to some degree shift here. The symplectic cohomology is given by the homology of the free loop space. Sorry. I'm always going too fast, so feel free to interrupt as much as possible. Okay, so full homotopy is, I'm not going to, well, it's just, it's just a combination of the ideas that I call Morse homotopy and full homology. So indeed, I think as far as I remember, the purpose of Cohen-Jones-Siegel to begin with was to define the full homotopy type, not to recover the stable homotopy type of the manifold only. Okay. So there has been some recent interest full homotopy spectrum under certain assumptions. Under some technical assumptions, he constructed a spectrum that I called SHMS, the spectral symplectic cohomology. I denoted it in this way because it's the full homotopical version of the symplectic cohomology. So this is basic SHMS as the symplectic cohomology coefficients. So some expectations are, okay, so you of course expect a version of then you plug in a cotangent bundle to recover the loop space of free loop space of n. Of course, you add a base point and take base loop suspension spectrum. And another expectation is that this thing, you expect this thing to be equivalent to the topological Hochschild homology of a category enriched over the spectra. So this thing doesn't exist itself in the literature. Somebody, I think probably Tim had that down.
But I just kept, I keep hearing this now. Paper, is that?
He constructed the
So why did everyone suddenly start thinking that this became a theorem?
No, I didn't say this is a theorem. Which one? The theorem.
But it says theorem large.
That's his thesis. That's in MIT. You find it.
Oh, this is defined in his thesis?
Yeah. He also defined it by a category. He defined there is the even algebra. Still defined in his thesis.
Okay.
These two things are just expectations, so I don't think those are in the literature. I mean, this spectral lab category also is something. Anyway, so as a result of this two expectations, it's natural to actually expect this guy itself to carry a cyclotomic structure. Questions? Meaning a circle action, which is already a structure that you find on the non-spectral version and Frobenius maps. There are some implications to that. So take the main theorem. Okay, so cohomology is a cyclotomy. Cyclotopy in the sense that it's not actually the this spectrum is cyclotomic sphere, but instead a model on a homotopy equivalent model. So we construct an S1 action on this guy, a genuine action, not an action out of homotopy. And Frobenius maps from SH to SA, the homotopy fixed points of of the underlying CP action. Any questions? Okay, so we actually construct models for this guy with a genuine circle action using ideas of Seidel, Bourgeois, and some other stuff in the. Okay. Any questions about the main theorem or anything that I've spoken about so far?
Can I ask a question? So,
Sure.
for example, you have this Frobenius map defined from SHMS to itself, right? Basically, actually, it's a self map.
Yeah, I mean, almost itself. It's the homotopy fixed points, but yeah.
So my question is, for example, if we apply this Frobenius map over and over again, then we end up having a projective system kind of thing.
Yeah.
So in number theory, for example, this is an extremely important construction. So we have, how shall I say, a certain type of ring, and we apply P power map, Frobenius map to itself, and we form a projective system. And eventually, this construction gives the so-called the tilting construction of Schulze, for example. It is the modern version of Fontaine and Vinten-Berger's construction due to back to '19 objects here appearing under this.
Sorry.
Yeah. No. Yeah.
I'm not sure if I can't remember if it was projective or injective. I think it was projective. There's a construction. PRs, but so you can actually construct some like out of a cyclotomic spectrum. You can make an iterative application of the Frobenius map. I think that was how it was constructed, and you can construct some other spectrum with cyclotomic structure.
Right.
So it's, and let me try to remember. I think like this is something very structured. It's like, I think this is like a Diadone module or a module, like homotopy groups give you the Diadone modules corresponding to formal groups.
Well, most probably because they are kind of related to the Fontaine periodic period spaces and such things, I mean. So, yeah.
Thanks.
Yeah.
And then this construction was recently, not maybe so recently, but was used, for instance, in the case of DB-Kohov varieties over FP to recover some groups. I forgot the Martin-Maser groups, the formal groups, or their Diadone modules. Anyway. Yeah, so we construct models for this guy genuine circle action. And let me state some implications.
What's the Seidel's genuine circle action?
No, it's just I mean the idea is about defining using this S-infinity models. Using this
not really genuine action, right? That's also homotopy action. That's also homotopy action. Right? It's not really...
for instance, you take this. You take the Floer data parameterized by S-infinity, and then there's a circle action. I mean, and then you take, for instance, the orbits of this to define the equivariant symplectic cohomology. I mean, it's not the idea in.
Okay, so I see. So it's not, you take the correct resolution of the Floer
Yeah, so
co-chain, but the resolution takes into account. It's not just a purely algebraic thing, right? It's the resolution also has.
Yeah, but what I mean by this is
moduli.
that, you know, they use they use, for instance, recently, for instance, I think in Nick Wilkins' work with Slidell, he was taking this S-infinity family of Floer data and was considering circles, but circles were themselves generators there. So he was using this to define the equivariant symplectic cohomology. Equivariant symplectic cohomology.
I think I understand what you're saying. Okay.
It's equivariant symplectic cohomology is more like the orbit space in this case, rather than the symplectic cohomology with circle action itself.
Can I ask a question too? I'm sorry.
Sure.
Don't know this topic very well, but you have a genuine CP action, right? So you have a genuine CP fixed point spectrum that comes from those CP fixed points. So how does that compare to homotopy fixed points that you define here? They're not giving you same thing, I assume.
So I have a, yeah. So how does I think there's something funny. Initially, we thought that we actually had a genuine cyclotomic spectrum, but the construction of, I should say, the S1 action is genuine, but the cyclotomic spectrum is not genuine in the sense that we don't identify SH with the TP homotopy fixed points. I think in this case, the action is like in the models that we consider, the action is free, so there are no fixed points.
So they cannot be same, and that wouldn't give you the Frobenius maps that you want to look at CP fixed points. So you get nothing, I guess, from that when the action is free.
Yeah.
Okay, thank you. Thank you.
Thanks. Initially, we thought we actually were constructing a genuine cyclotomic spectrum. Here, only the circle action is genuine. But it comes across some major issues in symplectic geometry, some transversality issues, and we thought we had some tricks to get over them, but didn't work. So let me state some implications of the main theorem. Someone in the question? Okay. Okay, so I wrote this as a separate implication. Okay, so this is the standard symplectic cohomology with coefficients in FP bracket U, where U is a variable of degree 2. This guy carries a cyclotomic structure. Sorry. More generally, if you have a cyclotomic spectrum X, then the smash product of SH with X carries a cyclotomic structure. In the previous example, it was the Eilenberg-MacLane spectrum of this polynomial ring. And for instance, you can actually apply the homology in a tricky way to the Frobenius to obtain maps from SH to itself. And here, this is somehow orthogonal to the Frobenius maps, the stuff that we prioritize, but you get some maps related to the power maps. So the first one here that I mentioned is expected to be the topological Hochschild homology of the Rab-Fukaya category with coefficients in FP. And we hope actually to show this without waiting for the spectral version to appear. And the last map is a bit more puzzling for the moment. We expect this to be the power map in loop space. For I was gonna say for n, it's for this guy, and related to the power maps in algebra. Okay, I came to the most technical part, I think. Any other questions?
But any other implications that are not just saying these things exist, like some symplectic topology application or something like this?
You have some mirror symmetry applications in mind, but that all relies on showing this guy is THH.
Mirror symmetry applications is what can you say a little bit, because you
Maybe more in the last slide.
huh? Oh, it's on your last slide. Okay.
I think I wrote some stuff. Mirror symmetry implications in the sense that if this thing, like it of course has to rely on showing that the Hochschild homology of this guy is this SHM with coefficients in FP bracket Q. And once you have a mirror symmetry result, that also tells you, like arithmetic mirror symmetry result, that also tells you that in the mirror, the topological Hochschild homology is this guy, the symplectic homology with coefficients in this ring. And you can use the structures. For instance, you can relate the Hodge-Witt numbers on the mirror if there is an arithmetic mirror, of course. Okay. There isn't much in the last slide, maybe this time. So this thing is built from Hamiltonian orbits and holomorphic cylinders, as I mentioned. So I came to the construction, the first circle action part. So the naive idea is, to define the circle action, you rotate everything. Okay, but like you had Hamiltonian orbits. There was a picture, if you remember, there was like circles representing Hamiltonian orbits and the cylinders. So you rotate the circles and you rotate the cylinders, and then the construction of Cohen-Jones sigle can be done circle equivariantly too. So the naive idea actually to rotate everything to define the circle action, but that doesn't work. So for one thing is that the Hamiltonian itself is time dependent. And okay, so this is the lesser issue, I guess. So the orbits of the rotated Hamiltonian, and same with the holomorphic structure. I didn't mention this, but the holomorphic structure is actually dependent on the domain here of the point. And to overcome this, you choose a family of Hamiltonians parameterized by a space, a nice space with an S1 action, with a free S1 action, and that's constructible. So and which rotates simultaneously. Well, you choose the family of Hamiltonians that rotates on ES. Okay, so you essentially construct the fibration, an S1 equivariant bundle over S infinity with fibers isomorphic to this, and you denote it by, the difference here is just there's this subscript S. You denote it by SH over S. And we still need to develop a setting for fluoromotopy theory in the Morse bot setting, because because critical state was a union of circles, so it's not discrete. Okay, that's the circle action. And I won't say much about Frobenius map. So you define a map from this guy to this guy, you actually switch the models. So you replace the base S with another S prime. Doesn't matter because it's all all homotopy equivalent, but and you target the homotopy fixed points. Okay, homotopy fixed points just means the space of CP equivariant maps from S infinity to this guy here. Okay. Or equivalently, you use the adjunction, you define a map from S infinity smash this guy to SH lower S prime. And you also impose this to be circle equivariant, but the action is modified on this component. Okay, here the S prime, the base S prime, is another model for ES1. As I mentioned, it's just given by the base S cross S infinity, but you twist, you change the action on the first S. You act Z acts by Z to the P. So it's p-fold action. So, and okay, this is a bit sloppy, and you basically use this by counting, by not counting, but by using the moduli of cylinders, as I draw here. So you, as your input, you take an orbit from here, you take, say it's X, you take its p-fold cover, and your output is Y here, and you put an auxiliary mid-circle here, and you choose the data to be p-fold on the left of this p-fold circle, and you consider the holomorphic maps so that this, you consider the holomorphic maps from this cylinder, so that on this part of the cylinder everything is p-fold. So you know, when breaking happens, well, let me not say anything about that.
Can I ask a question? From this slide, it came to my mind. We have the notion of characteristic of a ring, for example, in algebra, or characteristic of a field. In this topological setting, is there something called characteristic?
Characteristic field, what's characteristic field or characteristic?
No. I mean, for example, a field has characteristic P. If
characteristic of a field, I see.
I mean, so that we have this Frobenius maps and so on in, right? I mean,
yeah. Example.
So topology is much more in that sense. How shall I put it? There is more space, so that there is Frobenius map for every.
Yes, but
for
the target of the Frobenius is not HCP but TCP actually. It's, our construction is a bit finer than that, and TCP is a bit hard to explain, but it's similar to the Tate cohomology or Tate homology or whatever it's called, Tate cohomology in algebra. For instance, if you have a commutative algebra, if you consider the you know, trivial CP action on that thing, the Tate construct, the Tate cohomology or homology, whatever, it's A over P times A. So it serves as the natural target of the P power map if you want it to be a ring homomorphism. So you can still define it, but.
Okay. Thank you. By CP, you mean cyclic group of P elements, right?
Yes.
Okay.
Okay. Questions? Okay, so last slide. So it's a bit foundational. This work is foundational for some other goals. So, you know, one goal is, of course, to prove that this guy is the topological Hochschild homology. And, you know, and the first thing itself is also topological Hochschild homology of the spectral 2-pi category when the letter appears in the literature. Finally, we actually have some idea on how to show this, but unfortunately, this guy is not here. You know, this guy is not around at this point. And another goal is, of course, to do this for closed symplectic manifolds. You know, describe cyclotomic spectra on quantum cohomology using Gromov-Witten theory. And you know, constructions like Dennis trace map from algebraic K-theory. Yeah, so So this is the answer to İlhan Hoca, I suppose. Yeah. And so we also have a whole set of mirror symmetry speculations. So sometimes the Fukaya category is the same as dB of a variety. And in this case, of course, the topological Hochschild homologies also agree and can be used to relate Gromov-Witten theory on symplectic manifold to lots of things that you can recover from the topological Hochschild homology, like the Weil zeta functions, the point counts, etc. And that's all.
Thank you very much, Barış. It's a very, very interesting talk. Meanwhile, let me ask you a question about the last slide. So here, X is a variety over
FP.
or FP, right? FP, finite field.
Yeah.
So this means that this Fukaya category kind of thing is not only considered for symplectic manifolds, huh?
Yeah, sorry. Yeah, so that's my poor writing. So the Fukaya category of the symplectic manifold is isomorphic to well, I mean, the symplectic manifold and the variety are not the same. I mean,
I see.
Yeah. So the first version, the first version of mirror symmetry is a duality between Calabi-Yau manifolds. The Fukaya category of a Calabi-Yau manifold is sometimes the same, sometimes expected to be the same as the Fukaya category of the mirror dual, not as the sorry, dB of the mirror dual Calabi-Yau.
And X here is how it is related suddenly, how it appears here, the variety over FP.
I mean, so how it appears here. So for instance, when you have, I mean, sorry.
I mean, if you can have a mirror over FP, then there is no, then you must be using, you must have an exact symplectic manifold.
Yeah, yeah.
Then there is no Gromov-Witten theory.
Yeah, I mean, sure.
So what's a realistic, you know, you can assume everything. Let's assume that everything can be true, then what would be an application where, like, if you have an actual, let's say, if you work over the Novikov field and use a characteristic P field as your base field,
yeah.
then is there anything?
Sorry, go ahead.
No, no, that's all.
Sorry, this was a bit maybe sloppy to write Gromov-Witten theory here. I mean, you can, of course, use the structures on symplectic cohomology. I mean, so one thing is, as you say, I think exact case provides the most examples, but there are also refinements. Right? You know, Yankee has done some of that. Right? Refinements beyond the exact case, you know, symplectic level. But yeah.
So that develop this symplectic manifold theory over, instead of a complex number field, say over some, I don't know, over p-adic field, for example, the Tate field. So we complete it and take algebraic closure of it. So it's a very rich field. It's the p-adic analog of complex numbers. Can one develop, or are there, do you know people working on p-adic version of such symplectic manifold theory?
I'm not aware of it. You probably can do something, but
there's nothing special about complex numbers for the symplectic manifold theory. So
I think also, I mean, the only thing maybe it's algebraically closed, I mean, and
I don't
just
maybe
that
I mean, there is a theory of there's an theory of algebraic symplectic varieties, but I think it's a lot more restrictive. right? There's notion of symplectic resolutions, even it is on characteristic 0, not over PDX. But I think the examples are a lot rare. But
Okay.
yeah, so I'm not aware of anyone actually doing some sort of rigid analytic version of that, or PDX version of that, unfortunately.
Oh, yeah.
But to go back to this other stuff about, I mean, yeah, so Gromov-Witten theory is a bit sloppy here, of course. I mean, but for instance, when you have the Fukaya category, same as dB of some mirror variety, could be singular, could be what's it called? Could be open, but then you, like in some cases you have some computations of the THH and related invariants on this side. You recover, for instance, some Poggi numbers, you recover some formal groups associated to varieties from such constructions. So what I mean by this slightly sloppy statement is that you may be able to, you may not maybe, like in some cases you will be able to relate those constructions to things that arise from the Frobenius action. Let's not say quantum cohomology, but symplectic cohomology.
Okay, I see. So from this, I understand that this Fukaya category is related to how shall I put it? Algebraic geometry in the sense of abelian algebraic geometry, let me say. So if one considers derived algebraic geometry of tau n and so on, do you think it would be, we would have such an equivalence?
If I consider derived algebraic
So
geometry.
derived Fukaya category, I don't know. I mean,
Yeah, derived algebraic geometry means derived varieties.
yeah, DG categories, for example.
Sure, I mean, categories always come with some structure relating to DG structures. DG category structures. It's an A-infinite category, but I mean, so it's in this sense, you can think of it as a non-commutative variety. Of course, this is a contentless statement because, you know, you define non-commutative variety to be an A-infinity category or a DG category. Share equivalent notions over characteristic zero. Equivalent to the coherence series on the derived sequence, I don't know. I would say probably, but cases.
Barış, can I ask a question?
Sure.
On the slide before this, or maybe before that, you construct a bundle over S infinity ES1 bundle. So that's your construction. Is it?
Yeah.
So this is not something comes from action, right? Like you construct these bundles with the purpose to get something by hand. Like, what is this bundle?
So first, I should say the bundle part is not true in the sense that we actually use Morse both functions on S as well, so it's not exactly correct. But I made this slip. But the bundle part, so it's more like you know, the main reason that we can't describe circle action on SHM is because, you know, I had this picture. You built this from Hamiltonian orbits and holomorphic cylinders, but when you rotate orbits, they are no longer orbits of the same Hamiltonian. They are orbits of the rotated Hamiltonian. So you instead choose the family of, but this construction doesn't actually depend on the Hamiltonian, right? SHM with coefficients in S doesn't depend on the Hamiltonian. Sorry. It doesn't, like, it's Because isomorphism or its homotopy type doesn't depend on the choice of quadratic Hamiltonian, and so you can choose a family of Hamiltonians parameterized by S, and that rotate with the S1 action.
Mhm.
In the sense that, like, you have this point and you choose an Hamiltonian, you use S1 action to go to another point on S infinity, you rotate the same Hamiltonian, and now every fiber you put a copy of this guy. This is a explanation. That's not what exactly doing. As I said, we are using Morse function on S as well, but that's constructing you a fibration with an S1 action over this guy. And the fibers are homotopy equivalent, but they are not the same.
It's not a bundle, I guess. It's what
Yeah, it's not.
there's vibration. Okay, thanks.
Yeah.
Our recording will soon stop, by the way.